All right, so this is a typical percent composition question, and it's asking for both the empirical and the molecular formula. And in order to solve for molecular formula, you need to know empirical formula first. Um, when you see these questions, especially these percents, what that should bring to your mind is cent 100. So what we're going to do is we're going to pretend that we have 100 grams of potassium, carbon, oxygen, but we just don't know what the ratio of these numbers are. But we know there's potassium, carbon, and oxygen. And we're going to pretend there's 100. And the reason we do that is if we know that potassium is at 47%, that means if there's 100 grams of it, that we have 47 grams of potassium. And if we keep that in mind, we see that 14.5 is for carbon. So that means that we have 14.5 grams of carbon. And our oxygen is going to be coming in at 38.5 grams for oxygen. And from here, we're going to put them all over 1 because we're going to convert these into moles. If we have 100 grams of this overall compound, then what that means is if we have 47 grams of potassium, that we can use its molar mass for potassium, which is 39 grams of potassium for every 1 mole of it. So if we have 47 grams in our possession and we know 39 grams is 1 mole, and we divide that, 47 divided by 39, it's 1.2 moles. I'm going to round up here because I got 1.205. And then let's do the same thing for carbon. Carbon is at 12 grams. Oh, let me put grams here. Grams of carbon gives you 1 mole. But we don't have 12 grams. We have more than that, actually. We have 14.5. And 14.5 divided by 12 is also going to give us 1.21 moles. This is not something that should scare you when you see like similar figures like this. And percent composition questions, that's quite common. And now we look at oxygen, which is 16 grams of oxygen for every 1 mole of oxygen. And when we divide 38.5 by 16, 38.5 divided by 16, we get 2.4 moles of oxygen, right? And this was carbon, and then this is potassium. And percent composition, or when they ask for empirical formula is the most simple ratio of elements compared to each other. So if I were to divide these all by the smallest mole count that we find here, which is 1.21, so 1.21, 1.21, 1.21, what I get is that potassium is coming in at a ratio of 1 to carbon's 1, but then oxygen comes in at 2. So for every 1 potassium you get 2 oxygens. But for every 1 potassium you get 1 carbon. That's what we just figured out here. And we use this here. You don't want to write it as K1C1. You can just see that it's KCO2. That's what your teachers will be looking for. But now we've found here is the empirical formula. And now we look at the second part of our question here, and they tell us that what is the molecular formula? And they let us know that this compound that we happen to know is at 166.22 grams per mole. We look at this one here, though, K plus C plus 2 oxygens. So potassium, once again, is 39 grams. So potassium's 39 plus carbon's 12 plus oxygen's 2 16s. And I get this compound coming in at 83 grams of KCO2 gives me 1 mole of KCO2. But it's not supposed to be 83 grams. Our compound that we've just tested for is supposed to be 166.22. 166.22 grams per mole. Well, what is 83 compared to 166? It's actually doubled, right? We could check this by dividing, right? 166.22 divided by 83. It's going to be 2, which means that this molecule here, or more specifically this molecule here, everything needs to be doubled in order for its mass to match what we found to be in the lab as its true molar mass. So instead of K1, it's going to be K2, and then C gets doubled, and oxygen gets doubled, bringing it up to 4. And this here is the molecular formula. This is the actual formula that you're going to find this thing in nature. This is what it really looks like if you were to take one compound from, like, the air, or from the pile that you took it from, and you separated all the compounds in nature. This is what it looks like: 2 potassiums attached to 2 carbons attached to 4 oxygens. Best luck on your exams.